Okay, I think we have almost doubled the attendance in 5 minutes, so it's good time, I think, to start. Welcome to this session, which I have the pleasure of chairing together with Ian, who's replacing a colleague who had an accident just the day before coming. So all the best to Yosu, that was supposed to be co-chairing. Yeah, we are here to deal with an important topic for future of mobility in Europe, at large, that is batteries, but in particular here we're focusing on what is into the batteries. And of course that's the area where on one end we expect the innovation and the improvement of the batteries to come from, and at the same time is a very important element of the supply chain that for which in Europe we have already a presence. I mean, for the cells, complete cells, at the moment most of the production in Europe is actually made by people from outside Europe. While for the materials, anode and cathode and separators, we have excellences in Europe. So I think it's important to keep this capability, because they are supplying the battery manufacturers, the cell manufacturers, even abroad from technology developed in Europe. So it's very important that this is a continuing success story, hoping that projects like the ones that we're going to listen to are also paving the way for having the cells coming from European know-how. So I don't want to take too much time with this. I would like to start with the introduction of the speakers, that by accident, I think, we have two Italian ladies, even if they are working in completely different places. So it's well, it's a good sign that Europe is really, let's say, working in mixing the people and the knowledge and the academic careers across Europe. So I will start with Michele Ottaviani, who's a lecturer in physics at Limerick University. But, as I said, she started with a PhD at the Sapienza University of Rome, where she cooperated with another important institution, which is the Enea Research Center, which is the Energy Research Center in Italy. And she, with this experience, has become an expert in the synthesis of silicon-based nanomaterials for energy storage application. And she will present us the SI Drive project. The floor is yours.
Okay, so today I'm here for presenting you the SI Drive project. I am not the project coordinator, but I am in behalf of Professor Kevin. I am in behalf of Professor Kevin Ryan from the University of Limerick, that is the project coordinator, and more in general, I'm representing all the consortium of the SI Drive project. So, SI Drive project is based on an innovative chemistry. I will explain more in detail. It's an 8 million project that was developed for 4 years. Is involving 16 between industrial and academic partner. We are spread all around 7 different countries in Europe, and the leader of the project is the University of Limerick in Ireland. Regarding the innovative chemistry, the SI Drive project basically is based on lithium-rich cathode. We are having a polymer-based electrolyte, and we are using a nanostructure current collector that is 100% silicon-based. The vision of the SI Drive project is based on which are the future targets for the European community. So our main focus is to develop this new chemistry for the application of to the electric vehicle. So for us, it was really crucial to achieve a high energy density batteries with a longer cycle life, fast charging. But of course, because of the application of the electric vehicle, for us it was really crucial to to develop a very safe cell. So this was one of the targets. And the last but not the least, of course, our focus was also on the material recycling, always keeping in mind which are the targets that the European community is giving us for the future generation of the batteries. So the work package 1 is the work package that is working on the anode. The leader of the work package is the University of Limerick, and we are focused on developing the nanostructure current collector. This anode is 100% based on silicon that is deposited on a different kind of nanostructure current collector. Now, by starting from a lab scale, we reached the target that for us was having a structured electrode, silicon base, with the dimension of an A4 paper sheet. So we reached the target. In the picture I'm showing here, we went even a little bit beyond this target, because our aim is now to have the testing on the proper pouch cell. The strategies that we are using for this kind of chemistry is how we can tackle the very big problem we are having, that is the very strong capacity loss that we are having, especially when we are using a silicon-based anode. And the strategy is to use the lithium-rich cathode that are compensating, which is the capacity loss that we are having at the anode for the first discharge. The work package 2 is focused on the development of the ionic liquid-based electrolyte. This work package is led by the ENEA Research Center, and this was a very strong cooperation between the ENEA that found which was the optimal composition of the ionic liquid electrolyte that was allowing us to have the target of high current rates. So our target for this ionic liquid electrolyte was to have this kind of performances, but from the point of view of the safety, with the collaboration of the Politecnico di Torino, we were able to incorporate in a polymetric matrix this ionic liquid that the ENEA developed. Again, in this project, the aim is to develop full batteries that can work at large scale. So the target was to upscale also the quantity of the material that we were able to provide to our work packages partners. And this was also successfully achieved. Another important aspect of the cell chemistry was the cathode. This part is led from the KIT in Germany, and they were able to tackle the big problem of the cathode, that is how we can have a longer cycle life by keeping at least the 80% of the capacity retention. Here in this specific figure that I'm showing you, we achieve with a very high specific capacity, the 8% of capacity retention for the first 500 cycle. But as you can see, the prediction is that this kind of cathode could really reach the target of the project, that is 1,000 cycle, with the same kind of target in the capacity retention. How we tackle this problem? We basically develop different formulation of an artificial CEI layer. So basically a kind of protective layer that was enabling the cell to have a longer cycle life. This was the strategies. And what it was really impressive for us was to see how we achieve this kind of stability, and you can see the orange graph, within a 500 cycle, exactly using the ionic liquid formulation that was the successful one that the work package 2 developed. So the work package 2 found which was the optimal composition of this ionic liquid. And what it was really surprising for us, it was to see how this composition was working well. I didn't show the performance enough cell of the anode, but for both the anode and the cathode, we were having a very good performances with this kind of formulation that was identified within the work package 2. And again, here we are showing that we are having a cell stability within the first 500 cycle. Another target of the project was to find which was the optimal voltage window for having a cell that was working well, but it was maintaining the stability of the cell along a very big number of cycles. And this was another part of this study. And now here is explained why for us it was so crucial to use the polymeric matrix for our ionic liquid, because again, safety first. If we have to apply this kind of batteries in a real electric vehicle, this electrolyte cannot be flammable. And here there is a comparison of which is the standard electrolyte that is normally used, that is the LP30, that is the liquid one. And then in the comparison with the polymeric electrolyte we developed that is completely not flammable, and this was another goal for us. The very final goal for also this work package was to provide a bigger amount of material to give to our work package partner, and we successfully were able to achieve the 5 grams of material for the cathode side. Now we are basically at this stage of the project because we are having the leader of the work package 4, that is CITETEC in Spain, that is working on the harmonization of the full cell. So they are basically refining which are the working conditions for having a good performing full cell with the ionic liquid, the anode, and the cathode we selected as the most performing one. They compare the performances of this full cell with what we can consider a kind of reference that basically is a silicon graphite anode, that it was our reference, and the performance of the cell we developed, they are far beyond the capacity that we can achieve with a silicon graphite anode. So again, we confirm that a 100% silicon-based anode can really outstand the performance when compared to a silicon graphite anode. Here then they studied also different kind of pre-lithiation of the cathode with different formulation, again, with the aim of compensating the capacity loss of the anode and allowing to have a very good performing cell along a very long number of cycles. Another important aspect of the project for us was to how we can predict and understand what is happening at the micro scale inside our cells. So how the lithiation of the anode and the cathode can really affect which are the mechanical properties of our material. And now we are very lucky nowadays because we have all these simulation tools that they can really give us a very big help in terms of the prediction of which are the performances of our cell, because we all know that during the lithiation and the lithiation process that is happening cycling, we are having a very big mechanical stress, both of the anode and the cathode. And the simulation gives us a very good help in trying to understand which is the trend of our cell and in predicting which is the optimal cell design for having a better performances along the very long cycling process. And this work package is led by DLR, and they are guiding all this simulation part. Regarding, the final testing that now we are doing is within this work package that again is led by the CITETEC in Spain. They are working in collaboration with Zeta SW, and now they are working on this small prototype of pouch cell. These are 1 ampere hours pouch cell we are working at the moment, and they are working on which is the influence of the design for having the final optimal prototypes that can work well with our chemistry that we developed. Again, here the target was to have, first of all, a cycle life stability. So basically, they try to understand which was the optimal design for achieving this kind of target. And then, in collaboration with the Centro Ricerche Fiat, unfortunately, I cannot show you the very last results because they are still ongoing. They are working together with this small pouch cell prototype on fast charge protocol because, of course, for the final application of these batteries is also crucial to achieve a fast charging. Finally, but again, last but not least, the project is working also on understanding which is the feasibility of the recycling of this kind of cell. So in collaboration with the Leuven University, we are working for understanding, first of all, how we can disassemble the final cell we are having, how easy is the disassembling, and also if it is possible to recover the material that are inside the battery. So all the material of the anode, of the cathode, and all the part of the cell were analyzed for understanding the feasibility of the recycling process. So both these aspects, are still ongoing because we are at the final stage of the project. And of course, we now can say that we have the chemistry because we identified which is the optimal chemistry. At the moment, we are working on this small prototype, but of course, the vision of the SI drive is within the end of the project and beyond the project itself. Our dream is to find, after the completion of this testing we are doing on our prototype, to find industrial partners that are really interested on developing until the TRL9 level our chemistry, because at the moment, we are having a full prototype that is working, and we will be happy to complete the project beyond the project by having in mind the target 2030. So, again, I'm not repeating this part because it's almost the same. Our aim is to complete within 3 different phases. The first phase will be the refinement of the cell chemistry that we identified in collaboration with a proper industrial partner. The phase 2 will be the production upscaling, progressing from the TRL7 to the TRL9. That can be really the next target for the phase 3 that will be in 2030. And for me, that's all. I hope that my explanation gave you the idea of which is the project. These are all our contacts, and for having every other additional detail, you can have a look there. And,
Thank you very much for the very interesting presentation. For the second project we are going to look at, the project LISA, which is instead dealing with lithium sulfur. I will call on the stage the other speaker, Mrs. Palombarini, who has been graduated in chemistry from the Universidad Autónoma de Barcelona, but then had several other steps in both in electrochemistry and in a master in MBA. So, and now she's working in Leitat, where she has worked on the LISA project. So, the floor is yours.
Okay, so thank you so much for the nice introduction. I will explain a general overview of the last results of the LISA project, so lithium sulfur for safe road electrification. So this project has an EU contribution of almost 8 million euros, with the contribution of 2 universities, 3 research centers, and the rest of the partners, up to 13 partners from industries, so Varta, Accurec, etc. We had the collaboration of Oxys Energy from UK, but as most of you will know, unfortunately, they went to bankruptcy, so we needed to cover these activities of the final testing of the battery. And we were really lucky to incorporate Nextech Italy for the final cell production and testing. This project started in January 2019. It ended in December last year, so that's why I can show you the final results for this project. So to continue, the objectives of this project was basically to obtain a safe lithium sulfur battery to go beyond the standard operation. So this means abusive testing, thermal runaway, gas release, etc. To develop a layer-by-layer battery with a denser cathode with high sulfur utilization, obtaining more than 400 watt-hour per kg and 700 watt-hour per liter, with more than 1,000 cycles, to develop the state of charge and aging estimators, to validate the pulsed laser deposition for this layer-by-layer battery, and finally to assess the integration of this battery into e-bus and electric vehicles. So here I will give you a big overview of the timeline of the LISA project, so you to have an idea of how this project was built. So this project was built under the basis of another European project, which was called ALICE. Some of you will know because we have been collaborating with a large number of companies and entities. So with the ALICE project, we built a battery pack of 310 watt-hour per kg at 14 ampere-hour pouch cell level. Then when LISA started, through the entire 2020, we were able to reach a cathode allowing 400 watt-hour per kg at 18 ampere-hour cell level. So we reached one of the objectives with just 1 year of development. Then through the entire 2021, we lost Oxys Energy, but Nextech joined, and we were able to develop our first hybrid solid electrolyte on top of the separator, and we built our first generation of cylindrical pouch cells with with Varta. Then in January 2022, we reached 1,200 cycles at 50% of the dip of the charge, or more than 400 watt-hour per kg. So we reached 2 of our other KPIs. We built our next generation of cylindrical cells, and until the end of the project, we upscaled this hybrid solid electrolyte to be able to build the new generation of both cylindrical cells and also pouch cells. So if we go to the results in more detail, so here I'm showing you the first KPI achieved with the help of the Arkema and Oxys Energy companies. So in here, we were able to obtain a cathode with more than 70% of sulfur utilization, reaching between 400 and 410 watt-hour per kg. We upscaled this cathode up to more than 100 meters, and they were ready to be used. Regarding the lithium anode developed by pulsed laser deposition, so we were able to reduce the thickness of lithium up to 13 microns of lithium deposited on copper. This is a reduction of more than 20% coming from the commercial lithium that you can find. And in here I am showing you, this is a coin cell test level. So the comparison with the reference materials versus the 3 components developed at LISA project. So one is the cathode formulation developed between Oxys and Arkema, the coated separator with this hybrid solid electrolyte, and the lithium deposited on top of copper. So what you can see here is that the behavior of both cells are mostly the same with the reduction of lithium thickness. So this means reduction of weight and also volume. And this pulsed laser deposition is not only meant to be for only lithium, but also for the deposition of LGPS, so we can build this layer by layer battery of lithium sulfur. One question that I almost always get is, okay, so you say that LGPS can be done by pulsed laser deposition, but there are a lot of other methodologies where you can do it, for example, I don't know, sputtering or so on. And that is true. I mean, there are other methodologies that can be used to create this layer of LGPS. But there are 2 points that no one is taking into account. So the first one is that you can do very, very thin layers with pulsed laser deposition, and you can do this multi-layer of not only LGPS, but also lithium to obtain this multi-layer battery with pulsed laser deposition. So we reach this target to prove that it can be used to do this multi-layer system. Then moving on the project, in order to do this safer production battery, from the Fraunhofer Institute in Dresden, they proved that with this new solvent-free process, they were able to obtain these sulfur carbon composites to build the electrode. So no dryers are needed for that process, no toxic solvents are needed, actually no solvents at all. So it's all a solid process, so you reduce the fabrication cost up to 10%. This process was also evaluated at pouch cell level. Here you have some of the results. And it was also demonstrated for an all-solid state battery. If we move on to the hybrid solid electrolyte, here I am showing you, this was the first result. So this slide was shown last year by Christophe Rocher, so the guy I'm working with at LATAT. So you can see how the upscaling of the process was made, so this coating of the hybrid solid electrolyte on top of the separator. In here you can see that we have more than 200 cycles at coin cell level and 90 cycles at pouch cell level. But this was the first step, so no optimization of the process, not even for the upscaling of the hybrid solid electrolyte, and not for the pouch cell construction. Now I am able to show you the last results that we've got. So this is at pouch cell level evaluated with a 65% of sulfur utilization and the hybrid solid electrolyte upscaled. In here, you can see that we are able to reach more than 175 cycles, and these tests are ongoing. So the battery is not dead. So we will see how far we get with this new generation of battery. Then if we go to the cylindrical cells, here I'm showing you 2 of the generations that we built. One with liquid electrolyte, so this will be generation 1, and generation 2 with the hybrid solid electrolyte. Sorry, I cannot show you the long cycling test because they are still ongoing, but as you can see, capacity values are quite promising, and the behavior is almost the same at coin cell and pouch cell level. Okay, so now talking about what we got from the LISA project. So one of the achievements that we got was the knowledge about the pressure. So we know that for pouch cell systems, we need to apply some kind of pressure, but we didn't know, but by the beginning of the project, that that pressure was dependent on the electrolyte that we were using and on the cathode that we were using. So in here you can, if you want to know a little bit more about this, this was a paper published in the Journal of Physics. So in here you can see the comparison between two of the most used electrolytes in lithium sulfur batteries. So one is HMidol and the other one is diimidol. And you can see the difference on where do you need to apply pressure or not, and when it's beneficial to do it or not. Regarding the modeling side, so we were working with VDL to do this thermal assessment of the battery of lithium sulfur, because in order to apply it to the electric vehicles, this was an important thing to do. And we learned that we needed to add a cooling input to that thermal model to really simulate what was going on at real time. From the results coming from the Renault group, so this was another great achievement of the LISA project, because when we are going from the liquid system to the solid system, we all know that conductivity is always an issue, right? But we weren't aware that the lithium diffusion coefficient was something that we needed to really look into. And why is that? If you look the two graphs of the red one comparing to the green one, you will see that the conductivity is almost the same, but the diffusion coefficient of lithium really tackled the problem of the charging time of the battery. And this was something that, from the research point of view, we weren't aware of. We weren't looking for that. And from that point, we knew that this was something that we needed to take into account for the charging time, so to reduce it, so up to 30 minutes of charging time. For the state of charge and the state of aging algorithms, I won't stay here. Please forgive me about that. I'm not the modeling person to explain it, but from the Cranfield University, they did an amazing job with that. They have a lot of papers published, so you can find it in Batteries and Supercaps. And if you want more information, I can give you the contact. But they were developed and really studied with the real process of charging and aging of the batteries. And then, of course, we looked for a recycling process. That was one of the KPIs to look for. So for the selected LISA cell, we went through two options. So one was the low temperature, and the other one was the thermal deactivation. And at the end, we saw that with the thermal deactivation, we were able to achieve a more robust and safer process. One of the main drawbacks of going to this direction is that you cannot recover all the solvents, but it's, as I said, safer and more robust. So we went to that direction. And the overall recycling efficiency was proven to be almost 52%. With the obtain of sulfur as sulfate. I must say that, because one of the comments that I always get is, okay, but you are not obtaining the refining sulfur, so it's 49.4% if you consider a loss of sulfur refining process. Okay, so to finish, what's the impact of this obtained battery of lithium sulfur? So we can divide the impact in three parts. So first of all, it's the raw material, which it goes directly related to cost. So you know that price of cobalt and nickel has gone really, really far with the war and so on. So sulfur, it's really cheap. It's a byproduct of the oil industry, so really, really cheap. If we talk about lithium, which is the another part of it, well, we can say, okay, so maybe the transport, because it's not in Europe. Well, in Europe we have coming from Austria these days, so we have we have lithium just nearby in Europe, so we decrease the dependence of outside Europe of these materials. Then if we go through the safety part, I am quite sure that you all have seen this video of the needle test when you compare the needle testing of a common lithium ion and lithium sulfur battery. So with the needle test on a common lithium ion, it explodes. And if we go to the lithium sulfur battery, it doesn't explode. This, I must say, it's a liquid state, not solid state. But with this improvement just in liquid, so you can see the difference. And then if we go to the manufacturing process, so here in the LISA project, we have demonstrated that we can go to this dry process of roll-to-roll. So we don't need toxic solvents. We reduce the use of dryers, the use of electricity. So, and with this process, you can test different types of composites, so it's quite versatile. You can use it for whatever process you need. So with this one, we covered the three main parts of the impact of the LISA project. Regarding the applications, well, the lithium sulfur batteries has been already proven to be used in all of these applications where weight is not weight is the main issue, let's say, and you don't need high power. We know that power is the main issue still remaining for this technology and needs to be addressed in the upcoming years. To finish, just some dissemination and communication links for you to have. So we have plenty of publications. We have some prizes for the Young European Competition test. We did some radio release for the LISA project, so a lot of dissemination, 2 patents based off the upcoming projects, and some organized workshops where you can take a look on. So from my side, this is all. Thank you so much for listening, and if you have questions, I'll be more than happy to answer them.
Thank you very much for both interesting presentations, and I think we have plenty of time. I would pass the responsibility for managing this time to Ian.
Thank you very much. First of all, thank you for 2 very excellent presentations. When I saw the presentations last night, I was thinking, wow, that's a lot of material, it's a lot of information. I hope we can digest it all because it's really full. So we're really going from top down to some of the details of the chemistry, which I really think is quite impressive. And it's also impressive to see that these are known chemistries, but now we're making really important steps into the future and showing the viability of these chemistries. And one thing I really want to mention is if you look at the slides very carefully at the very beginning, you see that with these projects, we're strengthening the European network of excellence, or research excellence, which is really quite valuable for all of us. So thank you for that. Thank you also for Lisa for taking the challenging step from, say, the coin cells to the 18650s. This is really worth mentioning. It's really quite valuable for all of us. As well as that I'm giving you a little bit of rundown now, summary, so you can prepare lots of questions for this presentation. The last presentations, we've been able to establish a nice dialogue and exchange between the presenters and the audience. So we'll get to that in a second, but let me finish the final summary, the short summary. What I also like to see, which is quite nice, is your planned exploitation. So you're both moving on a pathway to exploitation, which is really nice to see. With really consequent steps. And then what I was looking at when you did the presentation for SC Drive was also thinking about utilizing the IPCI that's coming up. Okay, so that's one real huge opportunity for us to connect your results to the IPCI. And I think the final, let's see, what was my final, the timeline is strengthening. And it's very nice to see that we're getting the topic of recycling on the roadmap. In the past, we've been looking at the manufacturing process, we've been looking at the testing process, validation process. And now really adding this dimension of recycling is very, very important for us. So now I'd like to open the floor to lots of really good questions for our two presenters and to a nice dialogue with everybody here. So we have, I see at least 3 hands, 4 hands.
Thank you very much. Marco Tella from Extremion Human-Centric Digital Technologies. Very interesting presentation. I have a question for Flavio because I've heard news that looks like very interesting, and in particular it's contrasting the tons of bullshit that you see circulating on the social media, the playful one like Facebook, but also the serious, more serious like LinkedIn, and also many newspapers that pretend to be serious. So one of first is about the recyclability, as you have pointed out, and the second one is about the availability of materials because one of the biggest bullshit, there is not enough lithium, lithium is not available in Europe, is only in the country which are, let's say, exploiting low-cost labor, etc., etc., etc. So you mentioned that lithium has been discovered in Austria, is it correct?
Yes, yes. So there's one company, if I'm not mistaken, it's called European Leadership, something like that, in Austria. So they are aiming to be the leaders of providing lithium to Europe.
Very easy, because I live in Austria.
So, yes.
So there's more hands. So let's take the one closest to you. Oh, okay. And then we'll get to get to you.
Yes, and this is Anmar from Rice, Sweden. Congratulations for Bosch project. It's very nice, especially the two Bosch projects address the recycling issue along the project. This is really nice to hear this. And
Could you get close to the microphone, because otherwise the recording...
hello, can you hear me?
Yeah.
Yes. What I'm saying that I mean the integration of the recycling process into the work package in Bosch project is quite impressive and very nice to see. I have one question to Bosch project, especially one project is already finished, concluded, and how is this about this cost? I guess it's quite common that everybody starting presentation with 75 euro per kilowatt hour, and at the end no one really mentioned it. Then, so I'm just curious how this is going, especially with the first presentation. I expected this technology probably a bit expensive compared to other existing technologies today. So it would be nice if you can comment on it.
So yeah, I can answer. So within the work package that is doing the recycling aspect, they are also doing this kind of estimation. I don't have the number with me because it's not a work package that I'm dealing with, but the people that are working on the recycling on the cell, they are also giving us a precise estimation of which will be the cost of the final prototype. Because as you are correctly saying, this is something very important. So yeah, that's from our side.
Thank you. So from the lithium sulfur side, I have only the numbers, as I said, from the cathode side. So we know that with this new dry process, so with no solvents, no dryers and so on, so the reduction in price is almost 10%. Then we need, of course, to include it with the other processes and also including the life cycle assessment, because it's not just about the production, it's about what happens next if it goes to direct recycling of second application. But the final numbers with the entire process, I will be able to give it in a few weeks.
Carlos Agomailek from Ficosa. Thank you for the explanation. It's been very clear. Really, thank you. And I have a question. I come from the BMS sector, and so when I see this data, I start to think, how is going to affect us, this to the BMS? I mean, I'm seeing more stability in cells, so maybe there's no need of balancing, or maybe in the end, can we simplify BMSs if cells are as good as it's shown here?
I hope so. This is the aim of the project. I mean, now in particular for the SI Drive project, our next target would be to start working seriously with an industrial partner, because we want to tackle this specific aspect, because now we demonstrate at the lab scale that the prototype is working and is working accordingly to the target of the project. And first of all, it was the stability and good capacity retention even after a long number of cycles. So this is something very crucial in this moment for us, and we hope to answer soon to this question, if in the real world we can have the same performance we saw in the lab. That's the aim, so yeah.
Thank you, because when I see the other calls related with BMSs, we see a lot of movement in terms of data analysis and so on, and maybe we don't need that in the future. This is the reflection I'm starting to get from this presentation. Thank you.
More questions? Wolfgang. In the back, Wolfgang? Oh, I'm sorry. So we'll go.
Thank you.
The microphone.
Rémi Cornubert from Strat Anticipation. Thank you very much. It's good to see that Europe is working on the next generation of cell to capture leadership over countries outside Europe. I have two questions. The first one on G-Drive. How do you manage the swelling of the anode? Because when you have an anode which is made of silicon, that's a big issue. I guess this is because maybe you are using a nanostructure which facilitates the management.
Exactly. Our main outcome was that we are using a kind of three-dimensional structure. The first structure we synthesized was copper silicide nanowires. So basically we were having a copper current collector. We were directly using the copper coming from the substrate for growing these copper silicide nanowires. So first of all, we were ensuring that this kind of structure where we were depositing silicons was strongly attached to the substrate first. Second, because of the morphologies of this substrate, we were having enough space that was allowing this typical breathing of the silicon. In the second part of the project, when we did the proper scale-up, we were still using another kind of three-dimensional substrate that was a copper dendritic foil. So again, a three-dimensional structure that was very porous. And the deposition of silicon, it was not having any problem in terms of having enough space for the swelling. And so this was the very important aspect of the project. So having a 3D structure for allowing this. So it's not
the main breakthrough of this project, because if you manage to solve this issue, you can increase the capacity of
exactly. That's why we were able to use a 100% silicon-based anode, and we also increased the loading of silicon because of the morphology of the structure. This was the big achievement.
And my second question is on LISA, on the recycling process. I was wondering whether we should target a 100% recovery, because the main focus should be to recover 100% lithium, because sulphur is abundant and cheap. So I wanted to get your perspective on that.
Yeah, sure. The final goal is to increase recyclability, but one thing that LISA wasn't contemplating at that time when was built the project was the second application. But regarding the recovery of lithium, yes, we have other running project where the aim is to really recover it and selectively separate it from the final black mass. Yeah, it's going on.
Thank you.
Yeah,
Wolfgang.
Wolfgang Dittmann from Infineon. A similar question to the first one, to C-Drive, since we produce wafers, or we can etch wafers, and you have deposited silicon on copper, and afterwards structured it, or do you could imagine as well that you take a pre-structured in a wafer process silicon? So can you share a bit about thickness or?
Yeah, sure. Well, the thickness of the copper foil was a 16 micrometer foil. But here the key point is that we want to ensure a very good electric contact between which is the active material that is silicon and the substrate itself. So the strategy was to use directly the copper of the substrate for growing this kind of, I don't know, it's a three-dimensional structure that are a proper kind of forest of nanowires that we are growing by using directly the substrate. This was allowing us to not having the loss of the electric contact between the active material and the substrate. Regarding the deposition, we use the collaboration of one of our partners that is in Netherlands, that is the Smith Thermal, that is having at the industrial scale the opportunity of having the deposition of silicon with an optimized process they patented, that is a plasma-enhanced chemical vapor deposition, that is really effective, is really fast, because again, our aim was to move to an industrial scale. So we were having a very fast deposition, very effective, and we were able to increase from the very initial prototype that we're having at 0.25 mg of silicon per square centimeter to up to more than 1 mg per centimeter square for the final prototype. This was at the beginning just a kind of dreams, because we all know that the more you are increasing the quantity of silicon, the more the problem of the swelling is increasing. While by combining the expertise of this partner in terms of doing an effective deposition and the expertise of the University of Limerick in providing this kind of three-dimensional structure, we found the optimal morphology that was working well even with high loading. That's why we were able to achieve also high capacity in the cell. I don't know if I answer your question. Yeah. No worries.
More questions? I can see lots of questions in people's heads, but they have to get out into the room so we can address the questions.
I can fill in the time
Okay.
while people
we'll give you some more
are,
chances to give
people are
questions.
thinking. Yeah, your presentation brought to mind an old project I had, which was Helipos, and some of the partners are the same. And since we are here talking about materials, I remember that at that time, I'm talking about more than 10 years ago, the ionic liquids were a major problem. I remember our, let's say, old friend who unfortunately passed away, Mario Conte, who coordinated it. He said that there was one company in Japan that could deliver them in small quantities. And well, first of all, I'm not sure you're using the same type of, the same chemistry or slightly different and so on, but where are we in that story? Because at the time he said, yes, we might be successful, but then we have no way of producing it.
Well, actually, for this we have to thank the expertise of the ANEA Research Center, in particular Gianni Appetecchi, because he worked on the proper scale-up of this material. So not only he found the optimal composition of the ionic liquid, and for this detail we have to ask him because I am not working on this aspect, but was interesting to work also in upscaling the volume that we were able to provide. Now I cannot say how many liters because I don't know exactly the quantity, but I know that they strongly work on increasing this aspect. So I think this is now a problem that is no more as in the past.
So you're sourcing in Europe?
Yeah, exactly.
Oh, okay, very great.
Yeah.
So again to the audience, more questions? Yes, here. I do have lots of questions, so I can we can use the last half an hour, but I prefer to get it from the audience.
Yeah, I think the LISA project, one of the great achievements I can also highlight here was the dry processing electrode, which is fantastic. Just my question is that can you elaborate a little bit about this dry processing method that you have developed in the project, for example, in terms of the binder systems that you guys working on?
Well, I'm not the expert on that topic because Fraunhofer is the leader in that. But yeah, so every component that you use for your composite, it's on solid state. So you don't, as I said, because if you think about the binder on the common composites, either if you go for organic or aqueous binder, so for organic you have typical NMP with PDDF, for example, and so on. So now the binder, it's all solid state. So let's say that you include any type of carbon that you can imagine, sulfur, and then the binder solid, so no preparation needed before the preparation of the composite. And then it's basically a mixing of everything that it's optimized, of course, so you can have the proper composite homogeneity. And then it goes directly on the roll-to-roll process, and just by pressing, you got either you want on top of the aluminum carbon substrate or freestanding. So if you want, then well, the link is in the presentation, but we can talk as I have your contact, so we can talk and I will give you more details.
Thank you. More questions? I'm looking at everybody very carefully in the back of the room here. Okay, then I have to ask one of my favorite questions from the system point of view, and that is the question about C rates and fast charging. This is really a really important factor from the system side, that we have really fast charging is capable and maintaining lifetime. So we'll start with, should we go alphabetical or should we go? Okay, we'll go with Lisa first.
Yeah, don't worry. Okay, so for the charging time, as I said, we were closely working with Renault Group. So when they discovered this achievement that we needed to look for a new parameter in order to reduce the charging time, that's what we did. So the next step in the coming months would have been to optimize the final hybrid solid electrolyte to get the number of the lithium diffusion coefficient to reduce the charging time. Fortunately, I cannot give you the exact charging time of the battery right now because tests are ongoing, but at least the optimum system. And regarding the C rate testing, so well, the final cell is behaving at the same level than it was with the liquid system. So by that, we are not losing any capacity when hiring the C rate.
Okay, so what's the C rate right now?
We can go up to C, but the capacity, as I said, is the same when going with liquid, so it's reduced almost 60% of the initial capacity.
Yeah, we are almost in the same kind of stage because we are having now Centro Ricerche Fiat that with the prototype that Citatec is doing for us with the small pouch cell. They are working on this kind of fast charging protocol. We also demonstrate that we are able to achieve a 2C in terms of C rate with the Ionic liquids, but now the big challenge will be to move to the bigger scale pouch cell to see if this is still there. But the tests are ongoing, and is a Centro Ricerche Fiat that is doing this kind of testing on the fast charging. Yeah.
Thank you. I would say the next question would be for Lisa, and that is the Coulombic efficiencies. Do you see the potential to getting them up to 99.9%?
Well, with the optimized system, I do believe it's possible because as I show you, for at least for the cylindrical cells, we are almost there. So we did well, several cells, and most of them were between 96 and 98. So we are reaching that point. But yeah, we really need to see the final tests to see if we can keep it longer time. Yeah.
Okay, thank you. So everybody had a little break now from questions. Some questions from the audience? Mikhail? Okay.
Well, maybe.
No, I was just calling on him, but he doesn't have a question for today.
No, maybe just
We'll save it for next time.
a comment, maybe, because I saw that most of the questions from the public were related to the recycling process. So maybe to do a little bit of promotion of another European project, which is BATRO. So if you're interested in the recycling process, and mostly on the lithium recovery side. So we are working in the BATRO project, which most of the biggest industries in Europe to treat directly the black mass obtained from that, and also the recycling by design with them. So we're working closely with that. So I invite you all that are interested in that to have a look on the BATRO project.
If I may comment or maybe ask a question, there was this comment about, yeah, but sulfur is cheap, so it's not so important. On the other hand, how is it treated in the coming battery legislation, end of life? In the sense that I remember there was a debate on the fact that, yeah, but we should not, we should reduce anyway the volume of what we just burn, or so how is it matching with the expectation of the legislation?
Yeah, so I believe it's as any other material. So as far as you are able to treat it at the end of life and recover it and give it a second use, at the end it will match with the legislation, because you will not have issues with the clothing and the oil industry that is coming from, for example. So in that sense, if we are able to demonstrate, as we did in the LISA project, that you can reuse this material, it will match the legislation.
But even 50% or 60% that you are in, that would be sufficient?
Not now with the actual legislation, but as we are improving the system, we hope it will be, yeah.
And maybe today sulfur is a byproduct, but if we reduce oil, there will not be much byproduct. So we'll start.
Well, you can find it also in nature, so that's not the
I know.
issue. So.
We will need to reopen the mines in Sicily.
Yeah, exactly.
So more questions from the audience. Stefan.
Stefan Neugebauer, BMW. Can you give us a little bit more information about the costs? What do you expect, not only from single steps in the process or materials, but at the end, the overall total costs, if you really had a full battery use, which can be used in the vehicle, what do you think will be the result concerning the cost? Thank you.
So who wants to start?
Actually, we got a similar question before, and this aspect is still ongoing, because at the moment we are not having a full prediction of what will be the cost, because we are still working on a small prototype. But now we are studying a kind of a prevision of which will be the real cost of a real big battery. So this data I am still not having yet, because at the moment we are still on small prototype. But this is, of course, a very crucial aspect we will love to investigate.
Regarding the final LISA battery, I cannot give you a number, but for the ALICE project, which was the basis on what LISA was built upon, I will be happy to take your contacts, and I will give you the exact numbers of the full battery pack that was built for an EV car. So.
If I may, I think there are some, I understand it's very difficult because, well, you're basically electrochemist, and this is way in the chain. But at the same time, I think some comments you made, some results you had, hint at the fact that, well, first of all, you will have a higher density, and therefore, just by that, you are already cutting the cost. But I see very interesting the progress into safety, for instance. I mean, this might mean a simplification of the battery for cooling and so on, that could make a big impact. So the combination of the two, I mean, I have to report for the final session I think we have several aspects in each project that are really pointing, maybe not necessarily in some application that where high power is needed, for instance, yet, but sometimes I appreciate your intervention about all the stories going around. Even if this might be not yet mature for high-performance cars, it will still displace cobalt and other chemicals from other applications. So even if the maturity is not necessarily comparable to the best, but still it would help solve the issue, because you will be applicable for stationary whatever, where today it's lithium and it's cobalt and so on. So I think that the combination of these factors is making the whole package interesting.
Yeah, regarding the thermal assessment that you mentioned, yes, we went through so the liquid to solid, so we solved all the issues, thermal runaway systems that we found in the ALICE project, reaching really low and unusual temperatures here in Europe. So we solved the thermal issue with that, and so the entire I would say window of applications that we can see with the lithium sulfur battery. So you have heard that, for example, back in the 2019, Oxys was able to collaborate with different aerospace companies, so to build and to replace the common system with the lithium sulfur batteries, and the airplane was running. So we are going there to cover different applications. Yeah.
And I think from the comment you made about BMS, that's another simplification, that's another reduction of cost.
So, more questions? We have a question here.
Thank you. Maybe this question is for you, Maurizio. If we are very positive and we say these two projects they are key for Europe and they will reach TRL9, and then the question becomes how to make sure that we will industrialize this technology to have an asset in Europe, because I think it's I am clearly pro-European, but I think we are weak in this stage, because we have very good research. We have all the assets, public, private, to develop the next generation of batteries. But we need to make sure that we don't miss the industrialization. And just to give you an example, because I was astonished when I discovered that, when China decided 10 years ago to develop electrical vehicle, they look at the various electrochemistry. NCA was not possible because you have a lot of patents in Japan. NMC, same story with Korea. The only available electrochemistry was LFP, and they decided to put 30 billion, not million, 30 billion in 10 years to help Chinese players to develop and industrialize LFP. And now China is clearly the leader of LFP. So I just want to make sure that, and I'm sure you have an answer.
Well, it's not easy, but Ian already mentioned the ICPIs. The point is that I had a similar question yesterday. The European funding is supposed to be complementary to national funding. And because, you mentioned China. China is a country. So France is a country, not Europe yet. And so what we are trying to do is to complement. So the IPCI, for instance, allows to basically circumvent some limitations that would be legally there for member states to do this kind of investment. The other point, I think, is that these projects will, let's say, take or need to take those steps in the next few years. So I hope, cannot say more, that they come after the current generation of development. I remember speaking to one of the proposed gigafactory players in France, exactly, where I asked them, you are doing this basically on close to existing chemistry. Aren't you afraid that the other ones, which are not sleeping, come with the next step at that point? And the answer he gave was, I understand the risk, but for us, we have contracts, so we know that we can, and therefore, he says, we take this risk. So basically, these chemistries might be their next generation, and by that time, I hope that we have established sufficient mass manufacturing here, because the volumes need to grow fast, and talking to experts in the area also, they say, well, the Americans now are more attractive than us. So even we cannot even count on the fact that the Chinese or the Japanese or the Koreans will keep coming, because they're already here, but will do more in this kind of investment. So we have to make our share. I think the legislation, which is the thing which is more in our capacity, is there. There is, for sure, a need for, I think that there was a joke, I think I'm trying to translate it because it's in Italian. You know, there is a text was courageous captains, and these guys turn it into courageous capitals. Because that's, I mean, what you say is basically the fact that we are more risk averse than other places. Or, you mentioned China, or less, you know, just putting the money into things, knowing that part of it will be wasted. Because if you look at the funding the Chinese gave to car companies, how many are successful and how many went bust? There's a lot. But you know, they are saying, okay, I want to have 1, 2, 3, which become leaders. And there, I think BYD, for instance, is growing to a level where it starts to be needed to take notice as a minimum.
And maybe to add to that, what we're seeing here is a very good example of the proof of concept. What we're seeing here is really giving us an idea of what's going on with these chemistries, what is the potential of the chemistry, where are the risks behind the chemistries. So if we can synchronize these pathways with the IPCEI, then we're doing a great job. So we have to do the first industrialization with things we already know, but then transition to the things in the future like this. And as long as we're not too far away from in the manufacturing process, it'll be a nice transition. So I think that you know, now we're at the global galactic level and not down at the say how are we diffusing the silicium on the copper grid. So I'll pass the next question on to our colleague from Austria.
Well, I think you raised a very crucial point somehow. Regarding what are the investments for going into industrialization, because this, I think, it's very much connected with what is happening in this day. Last week I was at the KDT conference where there was triumph about the finally we got this CHIPS Act active. Well, 1 year ago, I was saying, are we really sure that we need a CHIPS Act in Europe or something like this? Because this is expected to tackle let's say, the shortage of semiconductor. And 2 days ago, I read on the Wall Street Journal that the shortage is becoming absolute. Shortage of semiconductor is becoming absolute. Now, with this CHIPS Act, we dropped the last fixed leaf about the fact that the European Union can support the industrialization. So all the projects we had to go to tier L 8.99999 and just touch the tier L9 because otherwise it was state aid, not anymore. So can we think about a kind of battery act in Europe that could eventually be as important, at least as important as the CHIPS Act? I leave this as of course we have some minutes left. I leave this as a food for thought and some provocation for the next steps.
So now we go from galactic to global galactic. I'll pass the question on to Maurizio.
Well, you know, there is something which is not specific for a sector, if you want, but is this debate on state aid, which is raging now. Of course, batteries would be one of the areas. I think that there is a difference there because, for instance, the CHIPS Act needs the investment for the factories. The point is that there, a European company is the best company into making the machines. So, for instance, there I'm really wondering whether there is a need also for, you know, a kind of we have to basically start discussing at a very high level where and how to avoid the exploitation of some capacities to impede others. I mean, one example which is often mentioned is the Chinese using their monopoly on rare earths, which is not a monopoly in terms of basic availability, but the point is that they have the whole chain, and therefore there was an example with Japan where they were disagreeing on something, on a few islands, and overnight they said, okay, I'm not providing you anymore the magnets. Now, maybe we should also consider this, saying, okay, I might not provide, which by the way is happening, the machines. So it's a tricky area because on one end you enter a sort of unfair competition which could trigger other consequences. So I say, yes, in principle it's possible, but there are many dimensions that need to be considered. And by the way, some of these dimensions are actually internal. Because, you know, Europe is split between those who say, yes, but if we leave freedom for all on state aid, then the ones which have more money for fiscal reasons will benefit more than those who don't. So some prefer that it's still a European dimension, and some would like a national dimension. And when you have this kind of strong differences, because it's not, you know, one country, it's a kind of group of countries in favor of one direction and on the other, I think that becomes highly political and not so much technical, let's say. Once this is solved, maybe then you have the agreement. And the example of the CHIPS Act for sure is a precedent.
And I think we also should be using the instruments we already have available. Simon Clark yesterday said that right now the culture and the environment for battery research is very, very good in Europe. So if we combine that with the IPCI, I think we're really very well positioned. So let's start with the tools we have now and work with them, and then see what the next step is, at least from my perspective. Any more questions? Let me check the time. 6 more minutes we have, or should we let everybody go to lunch early? I think I see a lot of people nodding that the idea of going to lunch is a very good idea. I would like to thank the speakers greatly for their wonderful presentations. And my co-moderator as well. Thank you, everybody. So everybody's released now for lunch officially.
Thank you, everybody, and enjoy lunch.